I'll go over. Okay.
Can you hear me at home?
Yes,
hear
you
you,
do
Ed.
very well.
It would have a green light. Yeah, that's good. Go ahead and talk and
Can the folks on Zoom hear me?
Yes, we're
Yes, I hear
zooming
you.
right past your words.
1, 2, 3, 4.
okay, we're getting a thumbs up.
Okay, good. All right, while he's getting the slides set up. One of the things that I've when I first started out, filters. Okay, wow, you got to grab 1 million filters, and light pollution filters. They're going to like fix my life, and everything's going to be perfect. And if I put nebula filters on, it's going to look like Hubble pictures, and wasn't quite the way I expected. But over time, I've learned to appreciate what these things can do. And I happen to be thinking about, I probably ought to learn more about these filters. And I get a call from this astronomy club up in Michigan, the Seven Ponds Astronomy Club, who I've done presentations for before. And they said, we've got a slot, do you have a presentation? I said, I was thinking about doing something on filters. So he goes, that'd be great. I said, okay, I guess I got to build a presentation for it now. So I did that for them in April. And then I was invited to do it here. So hopefully you get something out of it. And Ken, after you get that on, do I come over to the computer to turn it?
I can sit here and click if you.
I can do it. You can do it. Doesn't make any difference to me.
Yeah, I'll let you do it.
So you just want me to walk over to the computer to turn it, or you want to do it for me?
If it's easier, I can do it for you.
Do it for me.
Because you have these things to show.
Do it for me.
Okay,
Okay.
let me turn the lights down, or do you want to do this first?
No. This is during the presentation.
Oh, I won't turn them down too far.
It's all right.
Is that too dark?
Is that okay? All right, Ken, you can flip this over to the next slide. Okay, the one thing I'll point out here is we're talking about filters for visual astronomy. I'm not talking about astrophotography, although some of what we're going to discuss would apply. But the AP wizards in the room, if you want to jump in and make a comment how AP might be the same or different, feel free. So this is the agenda. Filters in general, where do they go in the light path? Solar filters, lunar, planetary, light pollution, nebula, aperture considerations, and we'll have a little summary at the end. All right, next one, Ken. So the first thing, which people who are first getting to astronomy do not necessarily realize, is filters never make anything brighter. Filters subtract light, they do not add it. So you'll hear people talking about how they put a filter in and something popped. Okay, it's not because it made that item brighter, it's because it made everything else dimmer. And the image that I use to describe this so that people will understand, go out on a bright day, light a candle and put it out in the middle of a football field. Then go stand by the goalpost. How noticeable is that candle? You probably wouldn't even know it was there if you hadn't put it there yourself. Now, do the same thing at midnight. And that candle will shine like a beacon. Why? It's not because the candle got brighter, it's because everything else got dimmer. All right. And that's contrast. And that's what filters do for us. They improve contrast. Filters selectively block light. They never make an object brighter. Some filters are broadband. We're going to be talking about broadband, narrowband, and line filters. Some targets are light sources, and some targets are light reflectors. And so as a result, you have different reasons for filtering and have different filtering effects. So you select the type of filter you're going to use based upon what you're viewing.
Oh,
All right, how are we doing?
we're good.
Okay, hit the next slide. So the first thing I want to go through, and some of what I have here on the table, is to talk about where filters go in the light path. You have aperture filters, And then you have filters that are down at the focuser end. All right. Ken, when I do the little stuff here, I'll walk over to the computer to make it easier for them to see.
Okay.
You can turn this. So first I'm going to look at filters at the focuser end, and I'm going to be doing some things here on the table. And for the people at home, as I'm doing this, I'll bring this over to the computer so you can see what we're talking about. So most of the filters that we use on a daily basis for nighttime observing go down at the focuser end. Eyepiece. Inside the eyepiece, there are threads. Okay, this is a 1 1/4 inch eyepiece, 1 1/4 inch filter. There's threads on the bottom of the filter. You can screw this on to the bottom of the eyepiece. And now when you put it in, you're looking at a filtered image. Okay, this happens to be a moon filter that I use on all my scopes. We'll talk more about them later. Now, if you put a filter on an eyepiece like this and you go, oh, that looks good, but I'd like to go to a higher magnification. All right. Unless you have a bunch of these, you've got to unscrew it off this one. Go get the next eyepiece, screw it onto that one, and you're in business again. How can you avoid so much screwing and unscrewing? Well, the first thing is you can put the eyepiece in, hold the filter over this end and look through. And you'll get an effect of what that's going to look like with the filter on it. So you can pop an eyepiece in, hold the filter, pop an eyepiece in, hold the filter. Okay, that's the magnification I want, screw it on. Everybody in this club knows that I'm a guy, I love zoom filters. Folks at home, do I need to come closer to the computer for you to see what I'm doing?
We're not getting the next slide.
I'm not hearing anything.
Anybody at home, should Ed come closer?
We don't see your slides.
You don't see the slide?
It's stuck. What
Says
slide?
it should be on filters at the focuser end.
Okay, so that's okay.
That's what I say.
Yeah, and now I'm doing a little demonstration here with some actual items. Can you see the cell where I'm in the picture?
I see it.
Red shirt?
Uh-huh.
If we
Okay, so that's me. They can only see me from here down, but that's all right. So that was how I was using a filter with a single fixed focus length, fixed focus eyepiece. I love zoom eyepieces. Okay, this is like having 4 or 5 eyepieces in one. And one of the reasons I like zoom eyepieces is because when I put this filter on this eyepiece, I can now go through a full range of magnifications from low to high and find exactly the right setting for this object with this filter. So I don't have to be swapping filters back and forth. Another way to use filters, this is a diagonal, okay, that you would have on your refractor or your SCT or whatever. This is threaded also. So what I can do is I can put the filter onto the diagonal and put this into the scope. And now every eyepiece I put in here will be benefiting from that filter. Just remember to take it off when you don't want to use that filter anymore. I've had sessions where I've done this, and then I put the telescope away, and I come out the next time, and it's, how come everything is so dim? Oh yeah, I got the nebula filter on there, and I'm trying to look at star clusters. All right. Now, what size filter? This is a 1.25 inch filter. Most of my filters are 1.25. However, filters also come in 2 inch. Now, obviously, where would you use a 2 inch filter? You'd use it on a 2 inch eyepiece. Screws on just like it would on a 1.25. However, if you have a 2 inch focuser, you probably have a 1.25 inch adapter. So you can use the smaller eyepieces in that big focuser. A lot of these adapters have threads in them. So I can screw the filter onto the adapter. And now when I'm swapping my 1.25 inch eyepieces, they all benefit from that filter. All right. One thing I would suggest is if you're going to do this, just to be sure, go do this during the day in the light, put the eyepieces in carefully. The probability that one of those eyepieces is going to hit that filter is very small. But you just spent $200 on the filter, and you're going to drop your 32 millimeter eyepiece in there, and you hear crack. You say, well, we found the rare one. All right. So even if you have mostly 1.25-inch eyepieces, if you have a scope that has an adapter on it like this, you might want to consider getting 2-inch filters, because this will work on your 2-inch eyepieces and it'll work on here for your 1.25s. Any questions? Any comments? I'll stop, every once in a while to ask so that, sure, Steve.
So on the back.
Let me give him a microphone.
Okay.
So, give the same example.
If you put the filter on the
Start
diagonal,
over. Yeah.
if you put the filter on the diagonal
Yes,
for the 2-inch, that would eliminate any possibility of it hitting.
if you have a 2-inch diagonal, yes, that would work
Well,
also.
I'm assuming you would because you have you're taking out the 1 1/4 inch.
I don't have a diagonal on my Dob,
That's,
but yes, if you have a 2-inch diagonal,
get rid of the top.
check to see if you have filters in it.
Any other questions?
Okay. Good comment. Good thing to point out. Go ahead, next one. All right. So this is what I just demonstrated for you by going through this on the table here. What size focuser, what size diagonal? What magnifications will you likely use? Well, you've either got to be swapping eyepieces and filters, using a zoom, or putting the filter on the diagonal or on the adapter. Does it have threads? 2-inch filter attached to a 1.25. So this is what I just went through with the actual devices. You can flip this. So first we're going to look at neutral density full spectrum filters. And we're going to start with solar filters. Next one, Ken. So what is a solar filter? Solar filters, and what we're going to talk about is white light filters first. Solar filters are typically used to observe the photosphere and sunspots. This would be an image of a type that you would see with a filter like this. It goes over the aperture. In the olden days, they used to make solar filters that you would attach to the eyepiece. If you have one of those, put it in the garbage, destroy it, or mount it as a historical piece, but don't use it. The reason being is that your telescope is gathering all this light, concentrating it down, and now this filter is trying to block it. Generates a truckload of heat and can cause that filter to fail. If it fails and that light comes through, you have this thing called blindness, which is something to be avoided. Okay. Think of looking at the sun, unshielded, no sunglasses, looking up at the sun. It hurts. Now imagine if you concentrated that a whole bunch. It would hurt a whole bunch. And for those of us who use magnifying glasses as kids to burn leaves and paper and what other cruel things we might have done, you don't want to be on the receiving end of that. So if you have one of those filters that goes on the eyepiece, do not use it.
You should show them the inside of that so they can see, because you held up the white part.
I'm going to get,
Oh,
I will, but I'm going to get to it.
okay.
Okay. Now filters can be coated glass or they can be Mylar film. Now I have, I didn't bring it with me, but I have a Mylar film made filter that I bought off of Amazon that I use on my 80 millimeter. Ken made this for me. He went and bought some Mylar film. This is a foam board, right?
Mount board, yeah.
Yeah, mount board. Cut a piece of the Mylar, glued it to this, put a second piece over it to give it some rigidity, And then he made a circle with some felt inside that would fit perfectly over my 5-inch Mac. Okay, so that I could use that for the two of us did an event with Malloy College when we had that 70% eclipse a couple of years ago. And so I had my ETX 80 and my ETX 125 tracking the sun. We never went total here, but people could see the sun being blocked out by by the moon. So it gave the effect. Now, these things are not expensive. If you have a telescope, you want to have a solar filter. Even if you went and bought one of these ready-made, Amazon, the camera store, one of the various astronomy, you can pick these things up for $15, $20, maybe $30. You can buy the film for maybe $7 or $8 and make your own. Okay, but Ken did a really nice job on making this one up. Fits perfectly on my Mac. He asked me, what's the diameter of the front of the thing? And he made the circle and put some felt in it, and it goes right on.
I used 2-ply mat board, cut 1.5-inch strips and wrapped it around and then taped it and then covered it with Elmer's glue and then wrapped another piece. So it's sort of paper plywood. There's like 3 layers
I'll
of.
let you take a look at this. I'll
Don't
ask
touch the
everyone,
Mylar.
don't touch the Mylar. Now, very important on solar filters. You get a scratch on this, you get a pinhole on it, you throw it away. Because not only does this block visible light, but it also blocks UV. All right, so you might look at it and you go, that little pinhole, I didn't know it'd be anything. But remember, your scope is concentrating that light. And so you do not want to use one of these things if it has a rip, if it has a scratch, if it has a pinhole. Before I use these, I kind of hold them up arm's length up to the sun, look around. I see anything, any place where light is leaking through. If it is, it goes right in the trash. You cannot fix them. And they're cheap enough that you shouldn't worry about it. Talking about your eyes. I tell you what, any that I have that are scratched up and ripped and torn, I'll give them to you. You can put tape on them. But you were asking how that was made. So you can pass that around. If you want to know how this was made, Ken made it for me. He did a beautiful job, so that's why I brought it. Okay, Ken, we can flip this.
Okay.
Now,
That thing at the bottom, I make sure it can't come off.
oh, very good point, Ken.
Well, you made the point.
yeah.
but-
But since I was talking about that, you'll see it in bold down on the bottom here, and Ken is right. These filters, solar filters, the aperture filters, unless you buy one that's made for your specific telescope, these things are more generic. It's an 80 millimeter, it's for 80 to 100 millimeters. They don't perfectly fit. And if they say it's a 100 millimeter filter, it's not the aperture of your scope they're talking about, it's the diameter of the front of the scope. So you have to go measure that front of the scope. And when you get it, chances are it's not going to fit perfectly, maybe even a little loose. Sometimes they'll have little screws on the side that you can clamp down to hold the filter. Even if you do that, put some tape on it. All right. Make sure that that thing cannot fall off. Again, you're down there looking, you're not looking at the filter. You're down there looking, a breeze comes by, off goes the filter. You're looking at the full blaze of the sun through an eyepiece on your telescope. You don't want to do that. So you want to make sure it can't fall off. Some of these Mylar filters produce a white image. Some of them produce a yellowish image. Doesn't have any effect on what you're looking at. I think that one gives me a white image. Ready-made size to fit over the front of the scope. Attach the edges, use tape, make sure it can't come off, and ensure there are no scratches and holes, as we said. All right, Ken, you can flip this. Ken, turn the slide.
I did. Right?
No?
We were there and right here.
Oh, I apologize, yes. There was a time when, and this goes back, chances are most of the people in the room never even heard of these things, but I wanted to bring it up. There was a time when people would say, oh, if you use exposed film, which, would come up dark, you can use that as a solar filter. No, you can't. Okay, because it may block a lot of light, but it doesn't block the UV. I remember when I was in elementary school, we had a solar eclipse coming through. We were making pinhole cameras, not pinhole, pinholes. Yeah, I guess it's called pinhole camera, where you would you pinhole it, you project it down so you could see it. But they were also telling us, or you could take like a piece of glass and smoke it with a candle, and you could use that as a solar filter. And people did that. And the logic today is don't do that. While I'm here, these are solar filters from my binoculars. Okay, so I can do solar observing with the binoculars. I bought these for the eclipse so that I could watch the eclipse progress. I think these were like $18 for the pair. And then I taped them on.
And those are Mylar?
Those are Mylar.
Right.
Now, one of the things that, again, have been cautioned is this filter material on this and the filter material on eclipse glasses, you've ever seen eclipse glasses, things like that, is different. Do not think that you are going to take those eclipse glasses and look down into an unfiltered telescope. That would be very dangerous. Okay, nor do you want to take those eclipse glasses and maybe somehow put them together and make a filter for your front of your scope. You don't want to do that. You want to buy purpose-made material. And it's so inexpensive, why take a chance? Next, Ken. Now, we've been talking about white light filters, inexpensive filters. Another way that you might want to observe the sun is in the hydrogen alpha spectrum. This is something that is more often used by the astrophotography people. However, you can visually observe the sun in hydrogen alpha. However, we're making this up as like $15 to $18. If you wanted to add, say, a Daystar Quark hydrogen alpha eyepiece to your scope, that's $1,295. Okay, this one is about $1,900, and that you got to be pretty dedicated in order to be adding a filter like that to your telescope. However, Mr. Filter in the back here, Tony, and I were having a discussion after the meeting one night about this. And he goes, yeah, these work. Yeah, they're fine. But you know what? Unless you're really serious into this, or you got some really high-end telescope that you want to leverage, what you really want, Ken, flip it, is this one, the Coronado. It's a 40 millimeter telescope. Now, remember, you're looking at the sun and we're blocking a lot of the light, so you don't need a big aperture. This is the Coronado PST Personal Solar Telescope. It's about $800. And Tony tells me it works really, really well. Yeah, I've never used one. I'm not a dedicated solar observer. I'll do white light so I can see sunspots and stuff. But this will allow you to see more of what's going on the surface. John?
The other alternative to that is the Lunt 40. That's better. Which is probably better and is better.
Comparable in price?
Yeah.
Really? Okay, good. So if you want to look at the sun in the hydrogen alpha range, and you're not using a high-end scope that, those two, the two that I showed earlier, and they're only for refractors. So if you're running an 8-inch diode, you're not going to use those hydrogen alpha filters. You're probably better off going to something like this as a first step. You get deep into this and you're starting to spy $5,000, $10,000 refractors, and you want to start putting filters on them. Have a great time. But this is a great way to get your feet into, because all the filtration system, all the filter system is built into the scope. You can't use this to look at the moon. You can't use this to look at star clusters. This is strictly for looking at the sun. Ken? Now, moon filters, lunar filters. The first thing I want to say about that is you do not need a filter to look at the moon. Looking at the moon with a filter is like putting on sunglasses. Okay, you're basically reducing the amount of light. Why? Because the moon can be very, very bright. You ever go take a look at the moon when it's at full, when it's full, and you go look in your scope and you go, ah. In addition, it completely kills your night vision. Okay, I've done this before where I said, oh, I don't have my filter with me. I'm going to go look at the full moon, and I look and hurts a little bit at first, but then my eye adjusts, and okay, I'm looking around, and I pick my head up, and I'm blind because it's dark, and my eye is now all clamped down because I've had this tremendous amount of light in, and I've got one eye that's open and one eye that's not. It's really weird. And so typically, if I'm looking at anything more than a first quarter or last quarter moon, I like to put a moon filter on, lunar filter. Now, these things come in various pass rates. So what this is 13%, 25%, 50% is how much light is this passing through. All right. So the lower the number, the less light it's passing through. Usually, or like sort of like the common wisdom was, if you had something less than 100 millimeters, then you'd want to be at a 25% or less reduction, say 25 or 50%. And if you're at a bigger scope, then you want to be like at a 13% filter.
Does that say on it like 0.3, 0.6, 0.9? How do they?
It says 25% on mine,
Oh, wow.
but some
Okay.
of them have a different
Sure.
numbering system.
And I always find best with variable polarizing filter. That's what I always do.
And we're going and Tony, you're right on it. All right. So I have a 25% filter that I bought for my 80 millimeter scope because that was my first scope. I use this on everything. I use it on my 12-inch Dob. And again, you don't have to use a lunar filter. The purpose here is to get the light down to a more comfortable level for your eye. And I personally feel like I get better contrast when I'm using a lunar filter. For any of you who are photographers, I know when I was working with DSLRs, you'd buy the camera, you'd buy the lens, and the very first thing you bought was a neutral density filter, okay, to protect the lens, okay? This doesn't add any color. It simply reduces the amount of light coming through. Now, you'll also see filters that are marked as moon and sky glow. Now, these are a little bit different. These also reduce the amount of light coming through from the moon, but they're also trying to reduce some of the light coming through from the glow in the sky. Some of it from man-made light pollution, some of it from natural sky glow. We're going to talk more about sky glow and light pollution later, but you will see moon filters, lunar filters, and you will also see lunar and sky glow filters. Okay. From a lunar point of view, I don't think they make a whole lot of difference. I don't see a lot of benefit from them for light pollution, but again, we'll talk more about that later, but you will see them labeled both ways. Ken? Oh, and as Tony mentioned, bring it back.
Okay.
13%, 25%, 50% pass through are very common and variable. The variable, if you ever taken two polarized sunglasses, held them up to each other and rotate them, okay, and you go from, hey, it's like there's two sunglasses here, okay, turn it this way and it goes black. So basically, what a variable filter for lunar is two polarized lenses, and you rotate them to give you the amount of blockage that you want. Okay.
I'd like to just add one thing.
Please.
You had suggested earlier taking a colored filter and putting that over the eyepiece. If you have a variable moon filter, do the same thing to tune it to the amount that you want to attenuate the light from, and then screw it on carefully.
Absolutely true. Yeah, it's something that I didn't realize when I first started. It never occurred to me to hold the filter over the eyepiece to look through. It was always screw it on, look, no, screw it off, go get the next one, screw it on, look, screw it off. And after a while, you go, these filters are a pain in the butt. I never even thought about putting them over the top, because then I got into zoom eyepieces and that fixed the problem. Next. Color filters for planets. Let's go. You'll see color filters, and they're almost exclusively used for planetary viewing. Is there any other application for colored filters other than planet? I haven't read about any, but any experience here? No, strictly planets. Okay. The idea of colored filters for planets is planets are reflectors, not light sources. So you've got essentially white light coming in from the sun, it hits the planets, it's getting reflected back. The reason my shirt is red is because it's reflecting red light, other light colors are being absorbed. All right. So if you're looking at Mars and Mars has that red-orange color to it, that's because that's predominantly what it's reflecting back. Other colors are being absorbed. What you can do with colored filters is change the degree of the colors that you're seeing off that planet. Again, Mars, Jupiter, Saturn. If you look at Jupiter through an eyepiece without a filter, okay, you see light bands and such. If you put colored filters onto them, what will happen is maybe you see no difference at all. Maybe you notice that along the edge of that cloud band, there's kind of a texture there you didn't notice before. So this is what I meant by the effects are subtle. So don't expect big results. I've spent whole nights floating through. I've got 6 colored filters. Now I have very cheap ones. These didn't cost much at all. And I've spent multiple nights like on Jupiter, on Saturn. Let's put the color in, take it off. Let's put a different color in, take it off. Making notes, what did I see that was different? And what happens is, if you look very carefully, you have to be patient. And as I said, okay, I see that cloud band. Now I put the filter in. I didn't notice it before, but there's kind of like a little streak running through that cloud band. I hadn't take the filter off. No, it's gone. Put it back on. Is it there? Yeah, it's there. You look at Mars. You use different filters and you'll go, okay, I see Mars, I see some darker areas, I see some lighter areas. Put the filter on. Oh, okay, that darker area is now more pronounced. Now, it's not like day and night. It's a matter of degree. If these things were expensive, I wouldn't have them and I wouldn't use them because the effects are fairly small. But these are sort of a low-end dyed filter. Yeah, I got a set of 4. You can buy a set of 4 of these for like $35 to $50. This is a blue filter. This is is this an ADA? This is an ADA. So this is one of the filters that I would use on Jupiter, for example. And I'll talk a little bit later about which filters work for which planets. Okay, and they make this by dyeing the lens. Now, Tony and I were, again, that same night, we were having a discussion about colored filters. Dyed filters, very inexpensive. There are much more expensive filters, Tony, which I presume would do a better job than these.
So I manufactured planetary filters, which nobody else did. And I was producing it for many years, but I decided to stop manufacturing it. I can do the more professional now, but I'm gonna go back and make them. They're
Yeah.
great.
Yeah.
I mean, they're very unique, but these are dyed filters of all different animals.
Yeah. So the thing that I would bring up to you is if you like to look at planets, planets is one of the things you like to focus on. For $35 to $50, you can get a set of 4 or 5, sometimes even 6 filters. It's worth playing with it. But the effect is going to be subtle because it's going to enhance certain colors, reduce others, and you may pick up a little thing here. I think when I was viewing Saturn, I could pick up a little better the separation in the rings. and I saw some characteristics on the planet that I couldn't see without the filter. But you had to look for it. It didn't jump out and smack me. I was on it for maybe 2 or 3 minutes before I actually noticed that I was seeing something with the filter that I wasn't seeing without it.
Color filters generally changes just the color. If you use yellow to make everything all yellow, use red to make everything all red. It's very, very generic, and I don't know, I haven't really seen it.
Yeah.
Advantage.
Like I said, it's something to, at low cost, it's something to play with. The one place where I will say is I haven't mentioned on this filter slide or the next one. The Ratten system, yes. Color filters are often described by a Ratten number. This comes out of photography. So you'll see it's a 21, it's a 23A, it's an 80A, it's an 82. If you go to your astronomy sites, you might see something that says this is a Jupiter filter. This is a Mars filter. What they're saying is that particular filter tends to bring value to that particular planet. 80A and 82A I have found useful on Jupiter and Saturn more than any of the other colors that I've used. Ken, you want to flip it? So here's just some general feelings for where these filters can be beneficial. And again, I just emphasize again, the effects are subtle. The yellow enhances red and orange features, often used on Mars, Jupiter, and Saturn. 21 reduces blue and green, which sometimes works well on Mars to improve the contrast between the light and dark areas. You can read the rest yourself. But as I was saying down here, 80A and 82A are both blue filters, and they're often sold under the names of Jupiter filters, Saturn filters. I find them, those are the 80 and the 82 are the ones that I use the most when I use them. You got it? All right, Ken, flip it. Light pollution, sky glow, and nebula filters. Everything we've talked about up to now is pretty easy to understand. You know, it's this filter blocks sun, this one reduces the glow of the moon. These colors will enhance a little bit on the planets. Here's where things get very, very tricky and very interesting. And that's when we start talking about light pollution and nebula filters. I was trying to think of how if I'd had a chalkboard or something, how I might, better describe this. But what I want to do is I want you to look at this particular diagram. What this is showing is that between 400 nanometers and 660 nanometers, we have this range of light. Okay, if you take a look on the side, it says that the human eye responds to about 380 to about 750 nanometers. Okay, that's the wavelength of the light. Okay, what we call colors. Okay, but they're what we see as colors are just a part of the overall spectrum of the electromagnetic spectrum. So what these filters do, these light pollution filters, these nebula filters, these line filters, is take this full spectrum and chop pieces out and block it. All right. So in this particular filter, this is a light pollution reduction filter. Not any particular one. This is just an example. Okay. Most of the light pollution falls into this range. This is where the wavelengths of that light that is preventing you from seeing those nebula, preventing you from seeing other things. And so this light pollution filter is trying to block some of that out while still allowing a lot of the rest of the spectrum through. All right. Now, when our what do you call it, street lights, and I'm getting ahead of myself here, but I might as well do it here. When our street lights were mercury vapor and sodium vapor, okay, those lights put out their street light, would put out their light in very, very specific wavelengths. Okay, and those are wavelengths that are not common on the deep sky objects that we want to look at. So you could go and put a filter together and they fell into this pocket. You put a filter together and you block that, and they can be very helpful. Now, what's happened over the years is that they've produced white LED streetlights now. Now, the white LED streetlights put out their light in the full spectrum. In other words, they're not narrow, they put it out all over. Very, very hard to block that out because some of that light is in the same wavelength as the things you want to look at. So those white streetlights have, in my opinion, made these light pollution reduction filters almost ineffective. Now, there are some situations, and I'll comment on them later, where they can be somewhat helpful, but not like they used to be. Tony, you got something to say? If anybody want to add anything to that?
Oh, I mean, I've used the white pollution filters, even with the LED light, and it definitely sort of improved it. So, I haven't really researched the LEDs enough to comment on it.
Okay. Now,
I'm all right about the sodium vapor, the other ones. The light pollution filters work very well for that, but, I'm not exactly sure the properties of the LEDs.
I had in front of my house, I have a problem where I live. I've got street lights all over the place. I've got a street light right in front of my house. I've got a commercial parking lot across the fence, all lit up. If I look out the other way, I've got Syosset Hospital and its building and all of its parking lot all lit up. And they were all sodium. And when I first started in astronomy 8 years ago, they were all sodium lights. And I started using these light pollution filters and they helped. It wasn't, panacea, but they helped. They've all been replaced by the white LEDs,
Oh, man.
all of them. And they're
Wow.
3 times as bright. And my light pollution filters now are in my not currently used box. So as we go through the discussion on these filters, and I just want to use these 3 illustrations. So here we have what would be referred to as a broadband filter. In other words, it's letting through a lot of the light spectrum, cutting out a relatively small amount. Here we're going to talk about a narrow band filter. Notice this is what's being let through. This is what's being blocked. All right, so much narrower. Down here we get to what's referred to as a line filter, even narrower than the narrow band. For those who don't know, certain elements produce their light in very, very narrow parts of the spectrum. Oxygen 3 is a common one that we use. Okay, and so you can filter out everything else except the light coming from oxygen 3. And we make use of that. So you'll hear me talk about broadband, narrow band, line filters as we go through the discussion. Ken, you want to flip that? So the components of sky glow. This is light pollution. Man-made lights, mercury vapor, sodium, incandescent bulbs, and now the white LEDs. Natural air glow. If we didn't have any man-made light at all, there would still be a glow in the sky, just from the natural light that comes through the atmosphere. And then there's light that's produced by interplanetary dust, unresolved starlight, zodiacal light. You go out into the country where there are no lights at all, it's not pitch black. There's light coming out of the sky and it makes the ground glow and it makes the air glow. All right, so this is what we refer to as sky glow. Filters attempt to deal with these sky glow components in various ways with various degrees of success. All right, so when Tony says that he's seen some positive effect from the light pollution filters, it's probably more of getting rid of these or reducing these than with the white LEDs. But I'm speculating. I'm not an authority on optics here. Ken, you want to flip it?
I'm still thinking that it's still gonna be better, I'll tell you why, for the emission nebula emits a certain amount of wavelength of light And the line filters you're talking about transmits that band that that they are emitting at.
Yep, you're about,
Everything else. So
you're-
it's probably, even with an LED, it's probably gonna work. It's gonna work much better.
you're 4 slides ahead of me. So, but I agree with you completely, but we're gonna focus in on that. So light pollution filters would be considered broadband filters. They're letting a lot of light through, but they are selectively blocking some of what we don't want. Flip. What? Go ahead. Okay. Now, where we get into the narrow band and line filters is in the area of what we refer to as nebula filters, okay, which is what Tony was just talking about. You have several types of nebula out there. Nebula, emission nebulas, it's a cloud of high temperature gas that is excited by emissions from nearby stars, works similar to a neon light. All right, and that puts out a certain kind of light. These are examples of emission nebula. Planetary nebula, a type of emission nebula, glowing shell of ionized gas ejected from a red giant star. Reminded early astronomers of planets because they tended to have a round shape. These are some examples of planetary nebula. Reflection nebula does not emit radiation of its own. It's reflecting light from another source. Dark nebula are clouds of dust that block the light from objects behind it. All right. So when you go observe things like this, I believe the Horsehead Nebula. If I got that one up there? No. Okay. I think the Horsehead Nebula is a dark nebula. Am I correct on that one? Yeah. Okay. So you don't actually see the Horsehead Nebula. You see all the light around it because the Horsehead Nebula blocks light coming through. Supernova remnants are the remains after a massive explosion known as a supernova. The cloud glows with the remains of the star that created it. And again, here's a couple of examples. Flip the slide. Now, the reason I wanted to describe the different kinds of nebula is because we talk about this is a nebula filter. This is a nebula filter. But this filter doesn't work as well on everything as perhaps this one does. And this one works on others better, but not all the same ones that this one works on. Okay, why? Because there are different kinds of nebula. They produce different kinds of light, and therefore different filters can have an advantage when looking at one versus another. Okay, nebula filters darken the sky to enhance contrast. Single line filters, usually oxygen 3 or hydrogen beta. Narrow band pass oxygen 3 and hydrogen beta. Broadband pass a wide range of frequencies. They can help, but usually not as effective as these two. Small aperture scopes may not work well with highly restrictive filters. Now, I've heard it said, well, you got to have an aperture of a certain size in order to use a nebula filter. It's probably true when you're giving guidance, but the fact is you can put any filter on any scope you want. If that nebula happens to be very, very bright and you're in a very dark area, putting that nebula filter on might work for you, but might not work very well at my house on an 80 millimeter scope, for example. I have my little ETX 80, and when I first put a nebula filter on it, it was like, there's nothing out there. If your scope's under 150 millimeters, see if you can try a friend's filter first. Okay. See what kind of effect you're going to get. And again, you take his filter and you just hold it over the eyepiece on yours and see if it enhances what you're looking at. Ken? Filter performance comparisons for some common nebula filter. This is a study that was done by Dave, is it Nicely? Is that how you pronounce his name? Nicely. He used Lumicon filters. Lumicon's a brand. And these were the Lumicon Deep Sky, which is a broadband filter. Remember, we talked about broadband before. Narrowband, which is the Lumicon Ultra High Contrast. And I'm going to focus in on that term later on. The Lumicon O3, which is a line filter, and the Lumicon H beta line filter. These would all be considered nebula filters. Okay. So what he did was he looked at a whole bunch of different nebula and rated how each filter worked on each individual nebula, each of these 4 filters. This is the summary. I have the report. It's, I don't know, it's probably 20 pages. But this comes off the summary. So the UHC, which is the narrow band filter, this is letting through oxygen 3 and hydrogen beta. This was the one that worked best, either the first or second best on the most objects. Oxygen 3 alone, which cuts out the hydrogen beta, was first or second on 56 of the objects. And it was not recommended on several. Hydrogen beta, first or second recommendation for only 18 objects, and not recommended on 39. Deep sky, which is that broadband filter, first or second recommendation on 10 objects only, with some slight improvement for the others. Now, remember, there's more than one kind of nebula. When he did this study, he was looking across all 4 types. His conclusion, so far, with a few notable exceptions, the numbers show that the UHC, and I'm going to convert that for you, is the narrow band filter. And the oxygen 3 are the filters of choice for viewing nebula, and to some degree supports the general recommendation that if only one filter can be purchased, it should be the narrow band filter that passes the oxygen 3 and the hydrogen beta. Okay? Or similar narrow band filters. Ken, flip the slide.
If I can offer one observation.
Please.
I have an 8-inch telescope and a 10-inch. They're both Newtonians. I use the UHC on both, but even up at Stellafane with the 8-inch scope, the O3 makes things so dark that, you know, unless I'm using the 10-inch scope, I don't bother. You may have different experiences, but the UHC is the one.
The Lumicon UHC?
Yeah,
Okay.
I have a couple of them, but
Okay.
the O3 really sucks a lot of light out.
Okay. Now remember that chart that I was showing you earlier, you know, up in the corner here? This is basically an explosion of something like that. So again, this blue line describes what we would refer to as these broadband filters, letting in a lot of light. It's not cutting out a huge amount of light. So it'll get rid of some of the sky glow, some of the light pollution. But if you're trying to see something that puts out a lot of light in this area only, then you want to get rid of as much of this as you can.
That broadband filter, if you put that in your telescope, the stars gonna look red. Transmit the red.
Okay,
It won't be natural. No.
who cares? Oh my God, all the stars turned red. It's coming to an end.
Don't wanna see something as natural as possible.
Well, yeah, but the point is this isn't going to be as effective on most nebula as the green one, the one that covers this. This is the narrow band. These are the 2 oxygen 3 lines. This is the hydrogen beta. The red one would be an oxygen 3 filter only. Ken, you want to flip it? Yeah.
Yeah, one other thing you might want to keep in mind is Nisley did that report quite some time ago. And Lumicon at that point in time was kind of a standard. Since that point in time, a number of other players have gotten into the game. So it really is kind of overdue to be redone. A, B, Lumicon has had variations in terms of the formula of each one of those filters. So depending upon what year you bought it, it'll probably differ from one that was made later. You know, at that point. So you've got now Botter, you've got Astronomic, you have a few other players that are making filters as good or probably better in some regards than any of the Lumicons.
I agree with you completely. And the purpose of this was not to say you got to buy Lumicon filters. But the reason he did it, as you read in the report, is if I use all Lumicon filters, which at the time was pretty much like the standard. This is the standard against which all others are measured. And if I do it all within the same manufacturer, then I don't have this business of manufacturer variation.
Yeah.
Now, what I want to zero in on right now, and this is something I discovered as I was putting this presentation together. The term UHC, ultra high contrast, is a name that was associated with that Lumicon narrowband filter. Okay, Lumicon never copyrighted it, they never trademarked it. And what's happened is other companies have come out now and said, this is our UHC filter, our ultra high contrast filter. So you go, okay, this says UHC filters, the best ones I should get because the Lumicon tested that way. I'm going to get Joe's UHC filter. It's going to be exactly the same. Not even close. I've run into this myself. UHC has become like saying Kleenex. Okay, everybody, you call Kmart's tissue box Kleenex. Okay, but it's not Kleenex. Flip it next. Ultra high contrast is an abused term. I tell you this because I don't want you to run out and buy something thinking you're going to get an effect that you don't get. UHC, term introduced by Lumicon years ago for their narrowband filter. Companies have taken it and applied it to a variety of filters that are broadband, not narrowband filters. Someone says you should get a UHC filter for nebula. They're most likely thinking of the Lumicon UHC or other narrowband filters. All right, not broadband. If it's called a UHC filter, read the fine print. I'll give you an example. I have one myself.
The UHC filters, when I design them, are designed for transmitting 3 different wavelengths. That's why it's UHC.
Yeah.
The terminology was defined a long time ago. Once it's designed, it's on 3 different wavelengths. But when I made my UHC filters, that they were square waves, they transmitted to 496, 501, and I think the other wavelength. And I was the first company to design it where I know you said about the red, I want things something natural looking. I eliminated that red. Now everybody has copied what I've done.
Okay.
So UHC's filters, because there's 3 wavelengths, that's why they called it UHC ultra high contrast.
Tony,
But that's the filters that are designed.
I agree with what you say about the filters that you made at the time you made them, but it is no longer true.
That's the thing.
I have a UHC filter here made by Opticon. Okay, this lets through a hell of a lot more than those 3 lines. Okay, this is actually what you would call a mid band. Now, I didn't know that when I bought it. Oh, it's absolutely UHC filter. It says so right here on the side. And you are making my point for me. Okay, I bought this thinking that this was a filter that was going to let through oxygen 3 and hydrogen beta.
It's easier to make the wider band filters, and they're using the terminology for sales.
That's it. Bingo, which is the whole reason.
Wider band filters are much easier to make.
Which is the whole reason why I'm talking about this, Tony. So, UHC filter is a common term. You talk to the guys who have been around forever, and you say, oh, gee, I'm going to buy my first nebula filter. What should I get? And you'll be told, oh, you want a UHC filter. All right. They're thinking about that narrow band filter that Lumicon made. Okay. Or other companies. I have where the heck is my, it's the DGM NPB, narrow passband, okay, which is a narrow band filter, similar to the Lumicon ultra high contrast. Orion makes one, they call it the Ultra Block. Okay, not quite as narrow as the Lumicon or the NPB, but still fairly narrow. So it cuts out all that other extraneous light that you don't want, and it works really well. It's about half the price. All right, but there's a lot of filters out there like this one which I didn't realize at the time, that are called UHC filters are not narrow band. This is absolutely not a narrow band filter. All right. I didn't know it at the time. There are resources available to help you see which ones are narrow, which ones are not. On cloudy nights, there is a fella who runs the company, Eyepieces ETC. Huh? Yeah. Yep.
What is-
Yeah. Yeah. So, well, it's not only buy it from him, but he has built a spreadsheet
Yes,
and he's published it.
but what he sells are the ones that he recommends.
I understand that.
John, what is the name of that?
Eyepieces, et cetera.
Oh, right.
By the way, in December, they're going to close.
Yeah, he's retiring.
Yeah. But the spreadsheets are still out there. And I make reference to it, I think, in the next slide, maybe. So when I started learning and preparing for this presentation, and I learned about this misuse of this UHC discussion, I'm going, well, how the hell do I know what the filters are? It says UHC on it. Some of these UHCs are barely more than that light pollution filter I showed you in the first one. All right, and you're going to go buy that and you're going to put, I got a UHC filter that hardly does anything. I mean, to see you, oh God, your UHC filter works great. How come mine sucks and yours is good? Okay, because mine is a narrow band and yours is a broadband. So don't go by this UHC term. What you want is a narrow band filter. Okay. I think I make reference to the that what do you call it, spreadsheet later. But if I didn't, when I send out, by the way, I'm going to send this presentation out tomorrow. Okay, I'll include the reference to this filter chart. All right. You got something else?
Yeah, so how they refer to the narrow, the UHC, the dual band.
So that's something different. Dual band of different wavelengths.
Yeah.
They do multiple wavelengths.
Yeah.
Narrow bands. That's
Yeah.
something different.
Yeah. So, next slide. If you, for example, I went out on Amazon and I was looking at SV Boni. Now, SV Boni is a sort of a lower priced astronomy products, but they've got some pretty good products. I'm not knocking them at all. And I looked at their UHC filter and it just described in there that it passes oxygen 3, H beta, H alpha, which you don't want in a narrow band filter, and yet they called it a UHC filter because it does enhance contrast, but it's not what you're looking for. All right, so here's the original Lumicon had a wave, a bandwidth. How much of the light spectrum did it pass? All right, remember we try to get this narrow little slit in the light spectrum. 26, that should be nanometers, NM. Okay, nanometer, NM, it's a typo. Now, Astronomic produces a UHCE filter, but it's what we would refer to as a wide narrow band, 45 nanometers. UHC-S by Beta, 61 nanometers wide. So these are letting through a whole lot of light that you don't want, that this one is blocking. And so on down. Here's the one that I was just holding. I thought I was buying something like this. I got this. Now, that doesn't mean it's a piece of garbage. Doesn't mean it doesn't work. I just got taken in by a term. Okay. But if I put this up on a nebula, it'll look better than it would without it. But it won't look as good as it would with that one. And so on down. So here are some examples of UHC. Yeah, the SV Boni UHC, narrow. It's a wide narrow, 50 nanometers. It's twice as wide as this one. So it's letting in all kinds of light that you don't want to have pass through. Tony.
Lumicon goes back to the 70s, and from what I remember, the guy was a well-educated guy that was into astronomy. Now, he didn't make filters. He contracted out the photo labs to do the filters, but he's the one that designed all the bandwidths and everything else like that back then. And he became very popular because they worked.
Yep.
They worked well. That Lumicon goes back in the 70s.
Yep.
but you know, when I design my filter, a lot of these guys are using it from marketing standpoints too.
Exactly. That's the whole point.
When I designed my filters, they were designed specifically the best observation for astronomy, for the wavelength that I made it for, and the bandwidth were picked specifically, and they work perfect. They work
Yeah,
perfectly.
But you don't make them anymore. Okay, next slide.
Not yet.
I love some of these transitions. They just,
I'm getting seasick.
when after I finish the whole deck, then it's like, let's put the transitions on. It just kind of makes it interesting. And I go, I love that one. So if you're going to go out and buy your first nebula filter, okay, as was done in the study and as I've seen with my own experience, these filters pass oxygen 3 and hydrogen beta. Lumicon, still a top name. The DGM is the company. NPB is narrow passband. Excellent reviews. I have this one. Eyepieces ETC, I think, is now the only company that sells them. I haven't been able to find them anyplace else. For a while, they didn't make them, and then they came out with them again, and he's got them. And the Orion Ultra Block, everything I've read from people who understand all this stuff is, you know, here we're talking about a filter that may be $150 for 1.25 inches. This is maybe $120. This one's about 80. And so if you're buying your first one, you don't have a big budget, you want to see how this helps, that Orion Ultra Block gets some pretty good reviews. All right, Ken? Now here's where a broadband filter can be helpful. And this is looking at galaxies. So this was, I don't remember which, I don't think it said which exact, oh, it's the Lumicon. It's the Lumicon Deep Sky filter, which if you remember from the earlier slide, is their broadband filter. So this is their equivalent of a light pollution filter. So this is roughly what the galaxy would look like without the filter. This is what the galaxy would look like with the filter. Now, no, this doesn't look like a Hubble photograph, but it does make a significant improvement. So these broadband filters have value, but that's not a nebula. That's a galaxy. Okay, Ken? Here's an example of what an oxygen 3 filter might do. Now, this is the Veil Nebula. Again, here's what it would look like without the filter. You see all the glow around it. This is what it might look like if you put the oxygen 3 filter in, because all you're letting through is the light that's being produced in the oxygen 3 band. And this particular nebula produces a lot of oxygen 3 light. And so the oxygen 3 filter works pretty well on this one. Next. Exit pupils and nebula filters. This is kind of an interesting thing that I didn't even know about until I started putting this presentation together. Okay, first of all, what is exit pupil? Exit pupil is the size of the cone of light coming out of the eyepiece. We can calculate that. We take the focal length of the eyepiece, divide it by the focal ratio of the scope, and that gives you the exit pupil in millimeters. So 38 millimeter eyepiece in an f6 scope will give you an exit pupil of 6.3 millimeters. The higher the magnification, the smaller the exit pupil. This is just mathematics. And there are exit pupil recommendations for various filters. This is from TeleView. This chart comes off the TeleView site. All right, where they're talking about what the average human eye pupil diameter is by age. As we get older, the iris of the eye can't open as much. All right. And so it has to do with how much light you can let into your eye. If you are 20 years old and you're out in a dark area and your eye gets fully dark adapted, your exit pupil, the opening of your eye might be around 8 millimeters. If I go out in a totally dark area and my eye completely opens up, the diameter of my pupil might be around 3.2 millimeters. Why is this important? Flip to the next slide. It has to do with how much light can get through into your eye. Okay, so they're talking about optimizing the exit pupil so that as much as possible of your retina is being illuminated. Okay, and since we're looking at things that are fairly dim, we don't want to lose any light. So again, going back to Lumicon, Lumicon says if you're using their deep sky filter, bandpass, they're recommending the optimum exit pupil, UHC, the optimum exit pupil is in that range, oxygen 3, H beta. Okay, so this has to do with selecting what's the optimum eyepiece that you're going to use to view this target. Okay, if you're getting down to an exit pupil of 0.5 millimeter on this one, you're probably not getting the best image. Right, Ken? Right. Aperture considerations. These are my scopes, or some of them. Solar filters work on all sizes of scopes. Often we stop down larger scopes. On my 12-inch, the dust cover here has a little thing I can pull off, and it makes a 2-inch aperture that's off center. And so if I was looking at the sun, I don't need a 12-inch solar filter. I only need a 2-inch solar filter because there's so much light coming in. Lunar and moon filters work on all sizes of scopes. But on the smaller scopes, you probably want to pass more light. So 25%, 50% might be your better choice, or a variable. Planet and nebula filters, these can block a lot of light. Is the scope gathering enough of the light you want to pass through? Trial and error are the best way to answer this. See if you can borrow a friend's filters, give them a try on your scope. Any filter can be used on any aperture, but the larger aperture, the better the view with these filters. All right, now this is that spreadsheet that I was talking about. And again, I'm going to send this out tomorrow. Eyepieces ETC, Don Penzick. He has a very good resource. It's an Excel spreadsheet. It lists pretty much all the filters available on the market, way beyond what he sells. And it will give you an assessment and the specifications for those filters. So this UH, that's where I came out earlier about which UHC filter had which pass. This is where it came from. And I completely trust Don. Don is absolutely trustworthy. You want to buy a filter and you want some really good advice, call this guy. Okay. And by the way, if he doesn't have what he thinks you should buy, he will tell you. Okay. I did that with him, and I've bought from him. And on a couple of occasions, he says, you know what you really want? You want this other thing, you know, and I don't have it, but this is what you're looking for. Absolutely solid guy. Too bad he's going to retire. So, summary here. Filters never make an object brighter. Filters selectively block light in order to enhance contrast. Some filters are broad spectrum, some broad spectrum, broadband. Some filters are narrow spectrum, narrow band. Some filters are line filters. Some targets are light sources. Some are reflectors. Some targets are light blockers. Again, we talked about the Horsehead Nebula. You select the type of filter based on what you're viewing. No single filter does it all. You will ultimately need a set. Okay. Thank you very much for your kind attention. And for those who dozed off, I didn't hear any snoring, so I thank you very much for that too. All right, any questions, comments?
Yeah. Howard, let me give you this is so people at home can hear your question.
Yeah, I had a question about the aperture for sun. And what I had done many years ago, I'm trying to remember, probably when Mercury was going across the face of the sun. I was using a 5-inch aperture telescope. I just put a black painted piece of plywood across the aperture and drilled some 1/4-inch holes around. And that seemed to work fairly well in terms that if you have a 5-inch aperture, it'd be 25 square inches roughly.
And you no filters?
No filter, because the ratio of the amount of open area compared to the 5-inch is like any one hole is a 4,000th roughly of what it would have been.
And what were you doing to filter out the ultraviolet light?
The ultraviolet light is filtered out by the same ratio. And if I remember right, I even put a very thin mask. I wasn't using an eyepiece. I was looking in the back of the telescope.
I don't know what to tell you, Howard. You obviously can see, so you're not blind.
That's
Okay.
not true.
Although I have seen you walk
That's
around
not
like this.
true. I'm half blind in one eye.
Okay.
And by the way, what you were saying about age and exit pupil is 100% right. Because I can certify that at the age of 86, the amount of light I need is significantly more than I needed when I was younger. Because your eye just does not open that wide.
Howard, I have no doubt that what you did worked. I wouldn't recommend it to anybody. Okay. And these are so cheap. I don't know why you would take the chance.
Years later, I bought one.
Oh, good, good. Any other questions, comments, personal experiences? Anyone want to do a song, a dance? Okay. Ta da 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 da. No, okay. All right.
Thank you. That was awesome.
Thank you all very much.
Thank you, sir. Thank you, sir. Sam, I have made you the moderator, the king. Oh, wait. Sam, you have to turn off the recording. I'm sorry. Are you there?
I'm here, but right now it's screen sharing, the slides.
Oh, okay. Let me do that. Stop.